Alright everyone, so we're now into the home stretch of the course. So we finished talking about derivatives and how we can use derivatives to do some problem solving and other applications for derivatives. And we're going to spend the last 3 days talking about how we can undo derivatives. So this is kind of an overview, a brief intro to some of the things you'll see in Calc 2. Okay, so we want to talk about undoing differentiation, so we should talk about how we undo other mathematical operations. So the simplest one is addition and subtraction. Right? So we add 3 to a number, we subtract 3, we get back what we started with. So that's kind of the idea that we want to aim for with undoing differentiation. The same thing works for multiplication and division. We multiply a number by 7, we divide a number by 7, we get back what we started with. Logarithms and exponentials work the same way. We take a number, we raise it to the power of e, we power it up by e, and then we take the natural logarithm of that expression, we get back the number we started with, right? So we have mathematical operations that we can undo. So we'd like to do the same thing here with derivatives. Okay, so we'll say that a function capital F is an antiderivative for little f on an interval I if if capital F prime is little f for every x in I. So in other words, we take the derivative of capital F, we get back little f. Okay, that's great. But there's one kind of key and also unfortunate word in here, and it's an. F of x is an antiderivative. If we were doing this with addition, we would, and we had a number x, we would say that, I don't know, y is an anti-addition or something, an anti-additive, something like that. The reason for this is that we kind of alluded to this at the end of the last video, is that if you have two functions and their derivatives are the same, the two functions can differ by a constant. So I could give you a whole bunch of different functions that all have the same derivative. And they could all be antiderivatives for some given function. So there's kind of that unfortunate thing. Okay, so let's go and find some antiderivatives. So we want to find an antiderivative for x squared. So in other words, we're trying to find a function so that when we take the derivative, we get x squared. Okay. So another way that you could think about this is we're kind of playing Jeopardy. So we're being given the answer and we need to come up with the question. Right? So one function that would satisfy this is x cubed over 3, because when you take that derivative, you'll clearly get x squared. But I could take x cubed over 3 plus 29. I could take x cubed over 3 minus 17, and so on. I could just add any constant I like, and I would still have an antiderivative. Okay, well, what about the square root of x? So we want to take some function, that when we take its derivative gives us x to the 1/2. Well, from what we know from the power rule, we're going to need something that has an x to the 3/2 in it. But then when we go and we take that constant and we put it out front, we'll get 3/2 multiplied out in front, which is 3/2 more than we'd like. So if we start with 2/3, x to the 3/2, when we multiply the 3/2 out in front, the 3/2 will cancel with the 2/3, giving us a coefficient of 1 out in front, and then we'll get that x to the 1/2. So 2/3 x to the 3/2 will do what we like here. Okay, well, what about 1 over x? Well, if you want to come up with a function that gives you the derivative 1 over x, well, natural logarithm suffices. Okay. Alright, so that leads us to the power rule for antiderivatives. So what we're going to do for an antiderivative is we're going to use this, this kind of stretched S symbol. So this says we are going to find the antiderivative of x to the p, and this dx means we're doing it with respect to x. The dx part becomes really, really important when you get into Calc 3, because there you can have functions of multiple variables, and then it's really important which variable you're taking the antiderivative with respect to. For us, we're only doing one variable, but you still need to include that dx part. Okay, so power rule in general. If you're looking for the antiderivative of x to the minus 1, then your antiderivative is natural logarithm of absolute value of x plus some arbitrary constant. The reason why it's absolute value is more because we want to allow for possibly negative values of x, because you could have negative values of x here, perfectly well defined, but if you had just natural logarithm of x, you wouldn't be able to have negative values of x. So minor problem there that we get around. Okay. But then in general, what we have for p not equal to 1 is we'll get x to the p plus 1 all divided by p plus 1 plus this arbitrary constant c. So the idea is this. We want to undo the power rule for derivatives, and what we have to do is undo each step in reverse order. Right, so remember that the power rule for derivatives, we took the exponent, we multiplied it out in front, and then we subtracted 1 from the exponent. So what we want to do is undo the steps in reverse order. Well, you undo subtracting by 1 by adding 1, and you undo multiplying by the exponent by dividing by the exponent. So what we're going to do for the power rule for antiderivatives is we're going to add 1 to the exponent and then divide by this new exponent. Okay, so a couple of rules that we could have. So we know that the derivative of a constant is 0. So if you want to find the antiderivative of 0, you get a constant. Right, so again, we're asking what function, when we take its derivative, gives us 0? Well, a constant. Does that make sense? If we have a constant multiple for an antiderivative, well, we know if we're trying to find the derivative of a constant times f of x, that's just our constant k times f prime. So if we're looking for the antiderivative of k times f, that's just k times the antiderivative of f. And then as we've had with limits and also derivatives, we can switch the order of taking addition and subtraction with, in this case, finding an antiderivative. Then we have a couple of special rules. The first two are fairly common. The third one's not really at all, but I just kind of include it for completeness. So if you want to find the antiderivative of e to the x, well, we said that e to the x is its own derivative, so the antiderivative of e to the x is also e to the x plus an arbitrary constant c. If you have e to the bx, well, we know that the derivative of e to the bx is b times e to the bx. So if you want to get the antiderivative of e to the bx, you'll get 1 over b e to the bx plus an arbitrary constant c. And then we have one for just an arbitrary power, so we have the antiderivative of a to the x, done with respect to x, is a to the x divided by natural logarithm of a plus our arbitrary constant c. Okay, so then there are a couple of trig rules. The main ones that you'd be expected to know are the sine and the cosine one. The other four, we don't really need to know now, and we also wouldn't be able to show where the other four come from. But sine and cosine, those ones you should know. So we know that the derivative of sine is cosine, but the antiderivative of sine is minus cosine. And also the derivative of cosine is minus sine, but the antiderivative of cosine is sine. Again, we're asking what function do we have to start with so that when we take the derivative, we get the thing that we're presented with. So if you're asking for a function that when you take its derivative gives you sine, you need minus cosine plus some arbitrary constant. Okay, so then we could ask, what is the antiderivative of sine divided by cosine squared? Well, if we're looking for the antiderivative of sine over cosine squared, we don't really have any tools that we've seen so far that are going to be of any use here. And it's not something clear from from the 6 I have listed here. But what we could do is we could go and look at the derivatives of trig functions. Right, and here we have is sine over cosine squared, and if we look at the derivative of secant, the derivative of secant is secant tangent. Well, secant is 1 over cosine, tangent is sine over cosine. So secant times tangent is going to be sine over cosine squared, which is exactly what we have here. So if we take the derivative of secant, we get sine over cosine squared. So the antiderivative of sine over cosine squared, dx, would be secant of x plus an arbitrary constant c. Okay, so then I'm going to wrap this one up by doing a very brief introduction to differential equations. So the idea in differential equations is that you want to find some function y which satisfies a set of conditions. Right, so for example, you might be asked to find a function y that satisfies the relation that y prime equals x squared plus x. Well, if you wanted to do that, we could just use our power rule for antiderivatives and come up with x cubed over 3 plus x squared over 2 plus c. And we'll call that a general solution because of that plus c. Now, you could also be asked to find a function y that satisfies a differential relation like this, but also you're given a point that you need the function to go through, and that's going to be able to get rid of the plus c and replace it with an actual number. Right, so if we wanted to find a function y so that y prime is x squared plus x and y of 0 is 1, we would find that y of x equal to x cubed over 3 plus x squared over 2 plus 1 is going to satisfy both of those conditions simultaneously. And we would call this y a particular solution, because there's exactly one of them. Okay, so 2 examples for this. So we want to find a function y prime, a function y so that y prime is equal to 3 over t plus 6 and y of 1 is equal to 8, and we're going to do this for t positive. Okay, so if we do that, we just have powers of t, so we're going to get a general solution of 3 natural logarithm of t, and because we're dealing with positive t, we can drop the absolute value signs, plus 6t plus some arbitrary constant. So that gives us our general solution. Now all we want to do is solve for the particular solution by applying the initial condition. So when we evaluate at t equals 1, we get 3 times natural logarithm of 1, well that's going to be 0, plus 6 times 1 plus c equals 8, so c equals 2. So that tells us the function 3 natural logarithm of t plus 6t plus 2 is going to satisfy the differential requirement and also the condition that y of 1 equals 8. Okay, so the second one that we want to do is we want to find a position function p so that the acceleration is 4, so the second derivative is 4, and the velocity at time 0 is minus 3, and the position at time 0 is 2. Okay, so we'll first go and find an antiderivative, and when we do that, we get that the velocity function will be 4t plus c, and we'll apply the initial condition that we have on the velocity function. So we're told that the velocity at time 0 has to be minus 3. That'll tell us that c has to be minus 3. And then we'll take the antiderivative of that, of our velocity function to get the position function. Because remember that the derivative of position is velocity, the second derivative of position, so the derivative of velocity is acceleration. So we'll get that our position function is going to be 2t squared minus 3t plus some other constant, and I'll call it k. And now we use our second initial condition, so the condition that the position at time 0 is 2. And when we do that, we find that k is 2. So our particular solution is going to be p equals 2t squared minus 3t plus 2. Okay, but you don't necessarily have to have your conditions be something about the position at time 0 and the velocity at time 0. You could have something like this where the position at time 0 is 2, but the position at some other points, in this case position at t equals 2, is 4. Okay, so we'll proceed as before. We'll find that our velocity function is going to be 4t plus c, but because we don't have any conditions on the velocity, we'll just have to take we'll have to antidifferentiate again. So we do that, we'll get that the position function is going to be 2t squared plus ct plus k. So we have two unknowns in the position function, but we conveniently have two conditions on the position function. So we can use the two conditions to solve for these two variables c and k. We'll first apply the initial condition at time 0, and that'll tell us that k equals 2. And when we apply the condition at time 2 and set that equal to 4, we'll see that c has to be equal to minus 3, and that'll give us the same particular solution as before, the position function of 2t squared minus 3t plus 2. Okay, so that gives us an introduction to antiderivatives and also a very, very brief look into differential equations. There's way more that could be said about that, but we really just don't have the tools to do too much with them. Okay, in the next video I'm going to do a bit of talking about some areas, and I will see you all then.